Hi everybody, I hope this video finds you well. In today's video, we're going to be introducing section 11.8 from your textbook, which takes us out of talking about numerical series, which was what we've been discussing from 11.2 to 11.7, to our next concept, which are power series. So in this video, we're going to give the definition of a power series, look at a couple examples in terms of just understanding what a power series is, and then start to actually study these power series with their first sort of major concept, which is what is called the interval of convergence. So let's go ahead and get started with a definition here. A power series is a series of the form sum a sub n x minus c to the n, where that a sub n is a sequence as usual, x is a variable, and c is a constant. So, a couple things about this in terms of how to think about this. One way that you can think about a power series is as a function that when you plug in a given x value gives you an infinite numeric series. So if you look at this definition, if you choose an x value and you plug in that x value, then what you're going to get is you're going to get a sub n times whatever you choose for x minus c raised to the nth power. And everything in here, once you pick a value for x, is going to just be numeric, and then you'll have an infinite series of those numeric values. So in other words, you can think about power series as something that when you choose an x value, it's sort of like a function, except its output is an infinite numeric series. The other way that you can think about power series, as we'll see in just a moment when we actually sort of write them out, is if you were actually to sort of write out what the first few terms would look like and imagine summing those together, you can actually think about a power series as an infinite version of a polynomial. And if you imagine these terms here, every time you choose a specific n power, so n equals 1, n equals 2, n equals 3, remember n is the index, so it's always going to be discrete. This type of term, remember, these a sub n's are just numbers, but these terms here are going to be x minus a constant raised to some exponent, and every one of those terms is going to be a polynomial. So in some ways, a power series is an infinite polynomial, right? We've encountered in our algebra careers many types of polynomials, quadratics, trinomials, linear functions, whatever. Now we're talking about the infinite extension of a polynomial. Last sort of quick note here before we just look at some examples is that value c in here, that x minus c, it's often referenced as the center of the power series. And we're going to see that it does play an important role, and it really does deserve that name of center there. So let's look at a couple examples of power series. So all of these below here, a, b, and c, and we'll take a look at each of them individually, are all power series. So this first one here, n equals 1 to infinity, 1 over n times x plus 4 to the n. If we were looking at this in terms of that sort of notation that we had up here, the a sub n would be that 1 over n. Right, that would be that sort of sequence value there. That x plus 4 to the n matches this. And of course, the center here would be negative 4. How do we know that that's negative 4? Well, because x plus 4 can be thought about as x minus negative 4. You can also think about the center as the value that when you were to plug it in here would give you 0. So this is something where the sequence is 1 over n and the center is c equals negative 4, just to make sure we're comfortable with the sort of terminology there. What would this look like if we expanded it out and actually wrote out the first few terms? Well, at n equals 1, it would be 1 over 1 times x plus 4. And then we do plus 1 over 2, x plus 4 squared. Then plus 1 over 3, x plus 4 cubed, plus ... And you can see when you really write it out like this, why we talk about a power series as an infinite version of a polynomial. Right? This right here, each of these individual terms, that's linear, that's quadratic, that's cubic, so on and so forth. We're adding all those together. We're getting this giant infinite polynomial there. All right, let's think a little bit about this part here. Again, we're just doing sort of a motivating example. We're not calculating anything here. But we also said that a power series really can be treated as a function, that when you plug in a given x value, you get an infinite numeric series. So let's imagine, just as some little mini examples here, what happens if we say, let's choose x equals negative 3. If we had x equals negative 3, just like a function, we'd plug that in, and what we would end up getting is the sum from n equals 1 to infinity, 1 over n, 1 to the n. And of course, if we simplified that, that would just be the sum from n equals 1 to infinity 1 over n. So when we choose a specific x value, we get just a standard numeric series, just a sum of a bunch of numbers. What happens if we let x be something else? Well, we'll get a different sort of value. Maybe we let x be negative 5. Then we would get something like n equals 1 infinity 1 over n. In here we'd get minus 1 to the n. And that would make it actually, I guess, be an alternating series, minus 1 to the n, 1 over n. Now, I chose x equals 3 and x equals minus 5 just to give you guys a couple, examples of what it means to plug in a value here. But I also chose minus 3 and minus 5 for another reason. You can see that when we let x equals minus 3, we get that harmonic series. And we know something about this. This is a series that diverges. And if you imagine, that would probably be a problem, right? Because that means you plug in an x value and you get a series that diverges. And remember, something that diverges isn't well defined. So you can sort of think about it, if you're really thinking about it as a function, that x equals minus 3 would not be a good input to put in. Because if we put it in, we get a series that diverges, something that's not well defined. But if we plug in x equals negative 5, we get that alternating harmonic, and we know from like the alternating series test that this actually converges. So it would be okay to go ahead and plug in x equals minus 5. The reason I'm mentioning that is because where we're sort of headed is to come up with what's called the interval of convergence. And the interval of convergence is the sort of domain of a power series. It's all the x values that when you plug them in actually give you a well-defined convergent infinite series. So this stuff is going to tie back into all the sort of stuff that we did about converging and diverging. The idea, though, here is that instead of having a single series, we have a series that really acts like a function. We get to choose x values, plug them in, and then the outputs are these infinite series. Of course, to be well-defined, we want infinite series that converge. Okay, let's take a look at another one. So this guy's a little bit different. N equals 1 to infinity, minus 1 to the n, 1 over 5 to the n, x minus 5 to the n. So here, the a sub n, well, that would be that minus 1 to the n, 1 over 5 to the n. That would be sort of the sequence component of it. Those are those terms here. And then this is the sort of power series component. The center here would be 5, because we have x minus 5. If we actually wrote out the first few terms, it would be something like negative 1/5 x minus 5, then plus, because it's going to alternate, 1 over 25 x minus 5 squared, then minus 1 over 125 x minus 5 cubed, and then plus dot, dot, dot. Once again, you can see that what I'm writing out, every one of these terms is polynomial, and this is really just one giant infinite polynomial. Again, I could imagine what happens if I let x be sort of different values. I won't do two of them this time, but again, just to sort of emphasize here, I don't know, let's say we let x equal, say, 1. Would that be a good input to use? Would that be valid? Is it going to give us a series that converges? Well, we can see if we plug in x equals 1, we'd get minus 1 to the n, 1 over 5 to the n, and we get minus 4 to the n there. Now that's pretty messy, but minus 1 to the n times minus 4 to the n, you can imagine that that would give us 4 to the n over 5 to the n. And that's actually not too bad. We could put that together and recognize that as 4 over 5 to the n. And actually, if we wanted to, we could actually figure out what that sums up to, because that's a convergent geometric series. This converges here. But what we're really going to be interested in, not only could I actually figure out the value of this one, the value here would be 1 over 1 minus 4/5 minus 1. And of course, it would be minus 1 because we started from n equals 1, not n equals 0. But what's really important is that putting in x equals 1 gives me a convergent series. It gives me a finite value. If I chose a different x value, you could show on your own, if you do like let x equal 100, you're going to get something that diverges, so that would be outside of our domain, outside that interval of convergence. Okay, let's take a look at one last one here. For this one, we have the sum from n equals 0 to infinity, x to the 2n over n factorial. We could rewrite this a little bit if it helps you sort of just visualize the different pieces. 1 over n factorial, and then x to the 2n separately. So here the a sub n component would be that 1 over n factorial. And the center here, well, keep in mind that that x could be written as x minus 0. So our center here would be c equals 0. If we actually wrote out the first few terms, we'd have to be a little lucky and sort of know that 0 factorial is equal to 1. That is a definition for factorials. 0 factorial is defined to be 1. So it looks like we get like 1 and then plus 1 over 1 x squared, and then we get 1 over 2 x to the 4th, and then 1 over 6, because 3 factorial is 6, x to the 6, plus dot, dot, dot. And so you would notice that this is once again all just a bunch of polynomials. Only little difference here is that that x to the 2n is only getting this sort of even exponents here. So this would be an only even degreed polynomial and infinite in nature. What about something like this in terms of interval of convergence? Well, we actually might think that this guy probably converges quite a bit, because if you think about choosing an x value, if I plug in an x value, this will be exponential. But one of the things we talked about in our summary in 11.7 is that factorials always outpace exponentials. So it almost won't matter what x value we plug in here. The presence of that n factorial in the denominator hopefully makes it converge. Now, we're not quite ready to talk about that just yet, so for now I'll just hold off, and I just wanted you guys to sort of see these first 3 examples of what do power series look like. Remember, you can think about power series as functions that when you plug in an x value, output an infinite series, or if you prefer, you can think about power series as infinite polynomials. And to be honest, we'll use both of those ways of thinking about them at different moments in our class. All right, what we're really interested, though, in now is getting ready to formally define this concept of the domain of a power series, the interval of the convergence. What sort of x values, like the ones we just happened to pick out here, are going to be allowed where we get an output that is a convergent series? Now, of course, in my first one, I just guessed a couple. One diverged, one converged. Here, I guessed one it happened to converge. And here, I sort of speculated maybe anything would work, but I didn't really check any. What we want to be able to do is that we want to be able to determine the interval of convergence based on the series. We don't want to do it by guessing and checking. We want to be able to actually computationally determine that interval. So let's go ahead and take a look at how we would do that. So, as we mentioned, similar to the concept of the domain of a function, we're going to be primarily interested in what is called the interval of convergence for a power series. The interval of convergence is the interval of all x values that, when plugged into our power series, gives us a numerical series that converges. Any x value you plug in is going to give you a numerical series, but the interval of convergence limits that to the x values that, when you plug them in, gives you a convergent series. That's why it's called the interval of convergence. In other words, you can think about the interval of convergence is the interval on which the power series is well defined. It's where you can plug in the x values, where you know the output is a well-defined output. As we will see as we do a couple examples, we can determine the interval of convergence by making use of our most recent test, the ratio and root test. There's one thing that we should know, though, before we get started at this. There's one value that always is going to make the power series converge, and that's the center, x equals c. So before we get into our examples, let's think about why at the center it is always going to converge. Well, if you go back to the definition of what a power series is, suppose you go ahead and you choose x equals c, and you plug that in. Well, by choosing x equals c, the inside of this is going to become 0 to the n, which is always just going to be 0. So that's going to cause all of these terms to just immediately become 0. And then we'll be summing up an infinite amount of zeros. Now, you might say to yourself, well, isn't summing up a bunch of infinitesimally small things in indeterminate form? Isn't that why we study series? And that's absolutely true. But if you plug in x equals c, these things aren't infinitesimally small. They're not really close to 0. They are 0. Like, they're literally 0. If they're not getting close to 0, they start and already are 0. So if you plug in x equals c, you will get a sum of all zeros, not a sum of things close to 0, but a sum of all zeros, and that is automatically going to converge. So for any power series, they always converge at their center. That's why that center value is very important. Okay, armed with that knowledge, let's go ahead and see how we would investigate the interval of convergence for some actual power series. So for our first example here, we've got this series, n equals 1 to infinity, 2 to the n over n squared x to the n. So let's make a little note at the beginning that the center is at x equals 0. We know that that is going to be part of our interval of convergence. Maybe that's all of our interval of convergence. Maybe that happens to be the only spot that it converges at, or maybe there's a whole range of values, but we know x equals 0 has to be included. So how are we going to investigate this? Well, we sort of gave the hint that we want to try to make use of ratio or root test. Since everything is just multiplied or divided here, distributing a 1 over n power shouldn't be too bad. So let's see if we can make use of root test. So we're going to try root test. So we're going to look at the limit as n goes to infinity of the absolute value of the terms here, which would be 2 to the n over n squared, x to the n, raised to the 1 over n. Right? In root test in general, you look at the absolute value of a sub n to the 1 over n. Here, our terms include that variable x there. Okay, now we need to be a little bit careful here. What we want to do is we want to sort of recognize that we can distribute this 1 over n onto each piece. But we got to be careful about these absolute value bars. If we think about these absolute value bars, this stuff here is assured to be positive. 2 to a positive power, that's going to be positive. N squared, that's positive. All this stuff is positive. But the absolute value might matter for that x to the n. So we're going to rewrite this first like this. We're going to look at this as limit as n goes to infinity. We can say that this is really 2 to the n over n squared. Absolute value doesn't really impact that. And we can say that this is the absolute value of x to the n. So the absolute value certainly might impact the x there because, again, we don't know what x is. We're trying to figure out what sort of x's make sense. And then we have our 1 over n up there. Okay, now we can go ahead and distribute this onto all the pieces. So we have our limit as n goes to infinity. Power to a power, we multiply, so we get 2 over n to the 2 over n. And then here we get absolute value x, because again, power to a power, you multiply the exponents. Okay, let's look at this and recognize that now after doing that simplification, this x doesn't have any n. In other words, the limit doesn't apply to this term. So if we want to, we can bring this out front. So we now have that this equals the absolute value of x, limit n goes to infinity, 2 over n, 2 over n. Now we can try to analyze this. Well, oftentimes with root test, we want to build something that looks like this, limit n goes to infinity, n to the 1 over n. So we can do that down here. So this is absolute value x, limit n goes to infinity, 2 over n to the 1 over n squared. Then we know that this limit goes to 1. So we can say this is absolute value x, limit n goes to infinity, 2 over 1 squared. And we get that that is absolute value x. I guess we don't really need the limit anymore here. So I guess get rid of that since we use the limit there, absolute value x. So we get absolute value x times 2. Okay, so we tried our root test. And we did all this stuff, and we came out that it comes out as absolute value of x times 2. Now you might look at that and say, okay, well what I'm supposed to do with root test is if this is less than 1, it converges, and if this is greater than 1, it diverges. But we don't know what this equals because we don't know what x is. But remember what we're trying to do here. We're trying to figure out the interval of convergence. So we want this to converge. So for this to converge, we want absolute value x times 2 to be less than 1. Right? That's what it means to converge under root test. You need that limit to be less than 1. Well, now we can solve that. That tells us that the absolute value of x needs to be less than 1/2. So what sort of interval are we describing? Well, it probably isn't necessary, but we can go ahead and draw a number line. There's 0, and there's 1/2, and there's minus 1/2. talking about absolute value of x being less than 1/2, that's describing everything between negative 1/2 to 1/2, all the x values who in absolute value are less than 1/2. If you remember from algebra, you can also write this as a double inequality, minus 1/2 less than x less than 1/2. You're fine to do that too, but you can also just sort of think about it visually. Okay, now that gives us a strong sort of picture of our interval of convergence. It converges in this range. If you're outside of the range, over here or over here, then you're going to diverge because this is going to be greater than 1. Now, there's a couple interesting things to talk about here. The first is that notice that the interval of convergence is, appropriately enough, centered at the center. X equals 0 is not only in our interval, which we knew it had to be because it had to converge at x equals 0 because that was the center, but it's actually in the middle of the interval. There's an equal amount of stuff here and here. So you can see again why we call that value the center. It's going to be at the center of the interval of convergence. The other thing is what happens at these endpoints. All right, so we got to figure out what happens at those two values, negative 1/2 and positive 1/2. Unfortunately, we can't make use of this because at x being negative 1/2 or x being 1/2, this absolute value x times 2 is going to be equal to 1, right? If x is 1/2, absolute value 1/2 times 2 is going to be equal to 1. Negative 1/2, absolute value of negative 1/2 is 1/2 times 2 is going to be equal to 1. And unfortunately, the root test doesn't give us any information when we have it equal to 1. Well, luckily, we can analyze that just directly by plugging in these endpoints. So let's give ourselves another page to sort of work at. Okay. So to handle the endpoints, plug them in directly. So one of the endpoints was x equals 1/2. So let's plug that in to our power series. So our power series was this 2 to the n over n squared x to the n. So let's plug in x equals 1/2. So if we do that, we would get the sum 2 to the n over n squared times 1/2 to the n. We're plugging in x equals 1/2 into our power series. Okay, now this is not a power series. This is just a normal numeric series, technically still from n equals 1 to infinity. So let's see if we can analyze what happens to this. Well, we can do a little bit of simplification first. 2 to the n times 1/2 to the n. That's going to be the sum from n equals 1 to infinity, 1 over n squared. And we know what happens with this. This converges as a p-series. So we've just figured out that at that endpoint, x equals 1/2, our power series still converges. So x equals 1/2 is part of our interval of convergence. What about x equals negative 1/2? Well, sum n equals 1 to infinity, 2 to the n, n squared, negative 1/2 to the n. Okay, that's plugging in x equals negative 1/2 into our power series. Multiply this with this, and we should get the sum n equals 1 to infinity, minus 1 to the n over n squared. Well, what do we know about this guy? Well, if you want, you could use AST on it, since it is alternating, or you could simply just put it in absolute value, recognize that it's this, and know that this is absolutely convergent. Either way, this also converges, either by AST or AC as p-series. Okay. Again, we just are interested in whether or not it converges or diverges, so we're not worrying so much about conditional or absolute convergence right now. We just wanted to know that if these endpoints converged. So both endpoints converged. That means in my little diagram, if there's 0, there's 1/2, there's negative 1/2, we know that it converged anywhere in here, but now we know it also converged at each endpoint. So we've just figured out that our interval of convergence, well, we can write it like a domain. It is negative 1/2 to 1/2. And we can put hard brackets on both of those because it includes both those endpoints. What we've just figured out here is if you choose any x value from negative 1/2 to 1/2, including negative 1/2 to 1/2, and you plug that x value into this, you will get a convergent series. So you can plug in 1/2, 1/3, negative 1/5, negative 3/8, whatever you like, as long as it's between negative 1/2 and 1/2. We've also learned a little bit more. We've also learned that if you go anything outside of this interval, you plug in 2, 3, negative 5, negative 1, whatever, anything outside this interval, when you plug that into your power series, you'll get a series that diverges. So the only x values that you can plug in that you're going to get a well-defined output for are x values between negative 1/2 and 1/2. Now, we're going to do more examples of this, but this process is going to remain very, very similar. We're going to always start when we're looking at the interval of convergence by identifying the center, then using either ratio or root test to get a sense of how large the interval should be. We're going to actually give that a name in our next video. We'll call this right here the radius of convergence. In other words, how far from the center to each endpoint. We'll define that formally in our next video. And then, if there are endpoints, we'll go ahead and test those endpoints individually. So this is a process that we're going to do a lot of. But for now, before we get to those more formal definitions, I'd like to go ahead and take a look at another example where something slightly different will happen. Same process, but slightly different result. So let's go ahead and look at this. We're going to try to determine the interval convergence for this power series. Okay, let's start the same way. Let's notice that our center here is at x equals negative 3. So we certainly know that that is going to be part of our interval of convergence. Once again, everything sort of nicely just multiplied or divided. So let's try root test again. So we're going to try root test. So we need to take the limit as n goes to infinity. We're going to put everything in there, 1 over n to the n, x plus 3 to the n in absolute value, then to the 1 over n. Once again, we'd like to distribute this on here, but we need to be careful. This absolute value might matter to that x plus 3, because the x plus 3 could theoretically be positive negative. We don't know anything about x. So we got to be a little careful. We're going to rewrite this. 1 over n to the n, that's got to be positive, so no absolute value bar is necessary there. But then x plus 3 in absolute value to the n. That absolute value might impact that x plus 3. And then all of that to the 1 over n. Okay, now we can go ahead and distribute our exponent. So power to a power we multiply, power to a power we multiply those exponents. So we get the limit as n goes to infinity, 1 over n, and an absolute value x plus 3. Then notice once again, this doesn't have anything to do with n, so this limit only applies here. We can pull this out front then. So we get absolute value x plus 3, limit n goes to infinity, 1 over n. Now, what do we know about this? Well, the limit is n goes to infinity of 1 over n. This is going to equal absolute value x plus 3 times, well, limit as n goes to infinity of 1 over n, 0. So we're going to get absolute value x plus 3 times 0. Now, you probably could just say that this is 0, but let's just hold off for a second. Let's do the same thing we did in the last one. For this to converge, right? For this to converge via root test, whatever we get here has to be less than 1. Absolute value x plus 3 times 0 has to be less than 1. Now, again, it's a little dumb that I'm writing times 0, but I want to write this statement out just to remind you that that's what root test says. Now, what do we know about this? Well, no matter what I pick for x, if I multiply it by 0, I'm definitely going to get something less than 1. So this is always true. No matter what x I pick, I add 3 to it, I take it in absolute value, I multiply it by 0, I'm going to get something less than 1. So this is always true. So what does this mean? Well, this means our interval of convergence is everything. It doesn't matter what x we pick. No matter what x we pick, this will always work. So how do we write everything or all real numbers as an interval? Well, that means our interval of convergence here would be negative infinity to positive infinity. It would be all real numbers. So we use the same approach here, but we got a sort of different result. The different result is that we didn't get a finite range. This would be a power series where its domain, or its interval of convergence, is everything. And the reason for that, if you think back to that sort of summary where we talked about the speeds of different expressions, when you pick out an x value, this term here becomes exponential. Exponentials are fast, but they're nowhere near as fast as that n to the n. So it doesn't matter what x you pick, this thing will converge. And that means our interval of convergence is everything. Computationally, you get an interval of convergence that is all real numbers when the limit becomes 0. Because if that limit becomes 0, then it doesn't matter what you pick for x, that will always be less than 1. Okay, so we definitely have encountered functions before that have full domains. Now we've seen that there are power series that also have full domains. Actually, one of my little examples here, we sort of briefly mentioned this guy. If you were to analyze this one, this would be another one that has an interval of convergence of negative infinity to infinity, because no matter what you pick for x, once you choose an x value, this becomes exponential in nature and the factorial much faster. If you want on your own, you can check that that guy right there also has an infinite interval of convergence. But let's try to take a look at one more example here. All right, so we're going to try to determine the interval of convergence for this power series. Notice that this power series, sum n equals 1 to infinity, n factorial, 100 to the n, x minus 2 to the n. We can make a note here. The center is at x equals 2 in this case. Notice that this time there is a factorial present, so we might want to try to use ratio test. So for ratio test, we're going to look at the limit as n goes to infinity, put this thing in absolute value, plug in n plus 1, so I guess it would be n plus 1 factorial over 100 to the n plus 1, x minus 2 to the n plus 1, divided by, now we're going to plug in n, so n factorial, divided by 100 to the n, and x minus 2 to the n. Okay, we can do a little bit of sort of manipulation. We can swing this guy up here and this guy down. So it looks like we'd have the limit as n goes to infinity, n plus 1 factorial, x minus 2 to the n plus 1, and then 100 to the n, divided by, looks like we have n factorial, x minus 2 to the n, and 100 to the n plus 1. Okay, notice I haven't messed around with these absolute value bars because we don't know what x is, so it might apply to some of the pieces. Before we start to do that, though, let's go ahead and simplify as much as we can here. So if we do that, we have the limit as n goes to infinity. This simplification we should be pretty used to. N factorial cancels with n plus 1 factorial and just leaves us an n plus 1. So we have an n plus 1 up top. X minus 2 to the n can cancel with x minus 2 to the n plus 1, and we are left with just an x minus 2 up top. And then 100 to the n can cancel with 100 to the n plus 1 and leave us with an 100 to the 1 power, or just an 100 in the denominator. Okay, now that things are much simpler, let's recognize that this absolute value bar applies to this, but this is always guaranteed to be positive. So we have the limit now as n goes to infinity, n plus 1 over 100 times the absolute value, x minus 2. Again, got to have those absolute value bars on here because we have no idea what x is. If x is like 1, then this is actually a negative number. Absolute value is going to make a difference. But definitely can just put the absolute value on here because this stuff is always positive. Once again, this limit is as n goes to infinity, so it applies to this, does not apply to this. Let's pop that out front. So we have absolute value, x minus 2, limit n goes to infinity, n plus 1 over 100. Okay, what happens with this limit? Well, as n goes to infinity, obviously 100 is a big number, but n plus 1 is just going to get larger and larger. This is going to go to x minus 2 times basically something that becomes infinite. Okay, we want, remember, for ratio test, for this to converge, this needs to be less than 1. So to converge, absolute value x minus 2 times infinity has to be less than 1. Well, if you pick out an x value, this will become a number, and a number times something infinite is not going to be less than 1. Unless, of course, the number you happen to pick out makes this exactly 0. So this is never true except at x equals 2. Right? This inequality here will never be true unless you happen to pick exactly the center, where this is 0, and then 0 times this thing that's tending towards infinity is going to automatically be 0. So this is only true at x equals 2. Remember, x equals 2, unsurprisingly, was our center. So our interval of convergence is just the single value x equals 2. Okay, so these three examples, it turns out, and this is going to be one of the major results we talk about in our next video, is that these three results are actually the only three possibilities when analyzing interval of convergence. Whenever you guys look at the interval of convergence of a power series, you are either going to find that the interval is finite, like this, and is centered at your center. So that is one possibility, like this here. Or, second possibility, you get an interval of convergence that is everything. Or third possibility, you get an interval of convergence that is literally just the single value at the center. It turns out those are the only three possibilities. What sort of dictates those? Well, it's all based on that limit. If that limit comes out as a finite value, then you will get a finite interval of convergence. If that limit comes out as 0, you will get an infinite interval of convergence. And if that limit comes out as infinity, you will get an interval of convergence that is just a single value. So we will be summarizing that and doing a bunch more examples of actually determining the interval of convergence in our next video.